Hello everyone, we are continuing the topic of operational amplifiers, and today we are going to look at two other functional circuits using op-amps. They are difference amplifier and the current source. We are also going to look at some large signal limitations of practical op-amps. So let's get started. Let's start with the difference amplifier. In the circuit, our goal is to find how Vout is related to V1 and V2. V1 is applied to the inverting terminal of op-amp through this resistor R1, and V2 is connected to the non-inverting terminal of op-amp through this resistive network of R2 and R3. So we're going to again assume that this is an ideal op-amp, and we're going to use the first and second golden rules of op-amp for this circuit. Using the first golden rule, we know that IN is almost equal to IP, that is equal to 0. And because there is negative feedback in this circuit, I can see that Vout is connected to the inverting terminal of op-amp through this RF resistor. I'm going to use the second golden rule of op-amp that states Vn is almost equal to Vp when there is a negative feedback present in the circuit. Now I'm going to write KCL at node N and node P and solve it for Vout and V1 and V2. So starting from node N, I have the current that flows in this direction plus the current that flows in this direction equals to the 0, and from there I have Vn minus V1 divided by R1 plus Vn minus Vout divided by Rf equals to 0 because In is equal to 0. Now I'm going to multiply both sides of this equation by Rf. From there, Rf divided by R1 multiplied by Vn minus Rf divided by R1 multiplied by V1 plus Vn equals to Vout. Now I have Vout equals to 1 plus Rf over R1 multiplied by Vn minus Rf over R1 multiplied by V1. Let's box this one. Now the KCL at node P is going to tell me that the current that flows in this direction plus the current that leaves the node at this direction plus this current is equal to 0 and IP is equal to 0. So from there, Vp over R3 plus Vp minus V2 over R2 is equal to 0. From there, R2 plus R3 divided by R2 times R3 multiplied by Vp equals to 1 V2 divided by R2. Now I'm going to write Vp equals to R3 divided by R2 plus R3 multiplied by V2. Now that I have Vp, because Vp and Vn are equal, this quantity and this quantity are equal, so I'm going to plug in this value, this quantity here, in Vn in the top equation and then find Vout as a function of V1 and V2. Let's do that. So Vout is going to be equal to negative Rf over R1 times V1 plus 1 plus Rf over R1 multiplied by R3 over R2 plus R3 multiplied by V2. If R3 over R2 equals to Rf over R1, if I choose the resistor such that this relationship holds, then Vout is going to be equal to Rf over R1 multiplied by difference of V2 minus V1. So I will, in this difference amplifier, the output is proportional to the difference of two input signals, V2 minus V1. The second functional circuit that we're going to look at is a transconductance amplifier or a current source. In this transconductance amplifier, the output current or IL is proportional to the input voltage, or VI. As a result, it's a transconductance amplifier. It also functions as a current source. That means IL, the output current of this op-amp, is independent of the value of RL, regardless of the load value that you connect to the output of this op-amp through these two terminals. Let's take a look and see, calculate IL and see how it works. So again, I'm going to use the first and second golden rule of op-amps. IN is almost equal to IP, that is equal to 0. I'm going to assume an ideal op-amp, also because there's negative feedback. There's this negative feedback network, and the output of the op-amp is connected through a resistive network to the inverting terminal of op-amp. From there, Vn is going to be equal to, almost equal to Vp. Now if I write Vn, the KCL at this node, I'm gonna have, this is my Vn, the current that flows in this direction equals to the current, let me delete this one, this equals to this IL. From there, Vn over R1 equals to IL. Vn and Vi are the same, so Vi over R1 equals to IL. So the load current is equal to Vi over R1, and it's not dependent on the value of load resistance or RL. As a result, it's a transconductance amplifier, and also operates as a current source because IL is going to be a fixed value that is independent of the load resistance value. One terminal of the load is connected to the output of the op-amp, and the other terminal is not connected to the ground, rather it's connected to the resistor R1 and the inverting terminal of the op-amp. Sometimes it's required to provide a current to a load that is grounded, and for that case we cannot use this current source. The second current source circuit, that is again based on op-amp, provides current for a load resistances that are grounded. As you can see here, RL is grounded, and this op-amp circuit is gonna function as a current source. Let's see how it works. Let's first label the currents in here. I'm gonna label this one IL, the current that flows through the load, and this one I1, this one I2, this one I3, and this one I4. The current that flows in this branch is going to be equal to I4 plus IL. Now I'm ready to solve the circuit. So I'm gonna first write KCL at this node and another KCL at this node. Again, we are going to assume that it is an ideal op-amp. Assume an ideal op-amp. From there, IN is almost equal to IP, that is equal to 0, and Vn is almost equal to Vp. Because I have this negative feedback, the output is connected to the inverting terminal through RF resistor. Then the KCL at node N at the inverting terminal is going to tell me that if I want to write it for I1, it's going to be 0 minus Vn divided by R1 is going to be equal to Vn minus Vout divided by Rf. From the other one at node P, Vi minus Vp divided by R2, this is my I3 current, is going to be equal to IL plus, now for I4 I'm going to write it as this node here, which is at Vp node, plus Vp minus Vout divided by R3. This is the value of I4. Now I'm going to write this second equation as, by replacing Vp with Vn, I'm going to write Vi minus Vn divided by R2 is going to be equal to IL plus Vn minus Vout divided by R3. Okay, so this is our equation 1, and this is equation 2. Now I'm going to name this parameter here as this expression here as B. This is the same expression. I'm gonna again name it B. So from this one I can see that negative Vn over R1 is going to be equal to B over Rf. Okay, now if we assume that, or if we select the resistors such that Rf over R1 would be equal to R3 over R2, then I have in here from equation 1 I have negative Vn over R1 equals to B over Rf. From there, negative Vn is going to be equal to B divided by Rf over R1, which is the same as I write B over R3 divided by R2 because of this choice of resistors. Now I'm going to use it to find the relationship between Vi and IL. So let's rewrite the second equation. If you do that, from the second equation we have Vi minus Vn divided by R2 equals to IL plus Vn minus Vout divided by R3. That is equal to IL plus B divided by R3. I named the expression of Vn minus Vout as B, and that's going to be equal to IL plus negative Vn divided by R2. So I have Vi divided by R2 minus Vn divided by R2 equals to IL plus negative Vn divided by R2. These two cancel out. From there, Vi divided by R2 is equal to IL. So as you can see, IL is proportional to Vi and it is independent of the value of the load resistor. So it's going to operate as a current source or a transconductance amplifier. The other part of this lecture is about the limitations of practical op-amps. We're going to look at two limitations. The first one is a voltage supply limit or saturation. Now the fact that the output voltage of a practical amplifier cannot exceed a certain threshold value, it is called saturation. So the output of op-amp circuit cannot exceed the level of external voltage supply that is connected to the op-amp, and it's generally slightly less than this voltage supply limit because some voltage is going to be dropped across the elements inside the op-amp. This maximum voltage value is called saturation voltage. So if you want the op-amp to operate in the linear region or operate as a linear amplifier such that Vout would be equal to AV times Vi, the output voltage should be less than V saturation from the positive side and greater than V saturation from the negative side. Consequently, Vin must be less than V saturation divided by the gain and must be greater than V negative saturation divided by AV. So any voltage level within these limits can be applied to the amplifier, and the amplifier is going to linearly amplify the signal. The second practical op-amp limitation is the maximum output current that you can get from the op-amp. Now a voltage amplifier model, if you remember, includes a voltage controlled voltage source in the output. Voltage sources generate a constant voltage level at the two output terminals of the voltage source regardless of the choice of the load that you connect to it. Now if you reduce the load resistance value, the voltage source is going to supply a larger current to maintain a constant voltage level at two terminals of the load. But in practical circuits, there is a limitation on how much current you can draw from an op-amp circuit. So if the circuit requires a larger current, the output voltage of the op-amp will saturate at the level corresponding to the maximum output current. Let's take a look at this example circuit that I provided here. This is this op-amp circuit in the inverting amplifier configuration. So I know the equation for Vout and Vi in this circuit. Vout is going to be equal to negative Rf, which is 10 kilo ohm, divided by R1, which is 1 kilo ohm, and that is multiplied by Vi, which is 1 volt in here. So Vout is going to be negative 10 volts as long as the amplifier operates in the linear region. Now, I also know that V out is equal to RL multiplied by IL, which is equal to RL multiplied by, using the KCL at the output node, I have IL equals to I out plus I2. So I2 and I out enter the node and IL leaves the node. Now, if I change the value of RL, or if I decrease the value of RL, to be able to maintain the constant negative 10 volts at the output, I out must increase. So if I decrease this one, because I want to keep I out at a constant level, if I decrease RL, I need the output current of op-amp is going to increase to maintain a constant voltage level at the output. But there is a limit on how much I can increase the I out value. When it hits a threshold value, the output of voltage of the op-amp is going to saturate. So this op-amp is going to be limited. The output of the op-amp is going to be limited by the maximum output current value. So today, in summary, we looked at two practical circuits or functional circuits using op-amps that were current source and a difference amplifier, and we looked at two limitations of op-amps in practical op-amps that were voltage supply limit and maximum output current limit. These are the only two limitations of practical op-amps that we're going to study in this course. There are some other limitations that you're going to see and study in future courses. Thank you.